This is Vamos, a polyphonic synthesizer we're building from scratch in C++20. It's inspired by Ableton's Drift and runs as a VST3 audio unit and standalone app. To make all that work across platforms, we use JUCE, the standard framework for building audio plugins. It handles plugin formats, the GUI, parameter management, and cross-platform audio. We combine it with CMake as our build system. Here's the signal flow we're building. Oscillators feed into a mixer through a filter shaped by an amplitude envelope and out to the speakers. Every block in this chain will code from scratch. In this episode, we lay the foundation, from project setup all the way to a working 8-voice synth plugin. 7 building blocks, one at a time. Before we write any audio code, we need a project structure that can produce VST3 audio unit and standalone builds from the same codebase. We use CMake with fetch content to pull in JUCE directly from its Git repository. This avoids the complexity of managing Git submodules or downloading frameworks by hand. CMake handles it all in one configure step. Our plugin targets 3 formats at once: VST3, audio unit, and standalone. JUCE wraps the platform-specific details. We just focus on writing the audio code, and JUCE makes sure it runs everywhere. One important architectural decision. We separate the project into 2 layers. The DSP layer is pure C++ with 0 JUCE dependencies. This means we can test oscillators, envelopes, and filters independently, without booting up the full plugin framework. The plugin layer then wires our DSP code to JUCE's audio processor for audio handling and its component system for the GUI. To generate any waveform, sine, saw, square, we need a single core mechanism. It's called a phasor, a phase accumulator that ramps from 0 to 1, then wraps around. Think of it as a clock that keeps ticking at a specific frequency. The speed is simply the frequency divided by the sample rate. The code is quite elegant. Each call to next advances the phase by the increment. When it passes 1, we subtract, creating an endlessly repeating ramp. That's the entire engine. From this single ramp, we derive every waveform. Multiply by 2 and subtract 1. You get a sawtooth. Pass it through a sine function, you get a sine wave. The phasor is the master clock for all of them. We have basic waveforms, but they don't sound clean yet. In this section, we'll fix that. A raw sawtooth has a hard jump at the wrap point, an instantaneous leap from +1 to -1. In the digital world, this sharp edge creates frequencies above what our sample rate can represent. Those frequencies fold back and appear as unwanted noise. This is called aliasing. The fix is called PolyBLEP, which stands for Polynomial Band Limited Step. The idea is straightforward. Instead of that hard jump, we gently round off the edges. Near the discontinuity, we apply a small correction that smooths the transition, like sanding down a sharp corner. The computational cost? Just 2 extra multiplications per sample. The result? A clean waveform without the aliasing artifacts. Here's the implementation. The PolyBLEP function checks if we're near the wrap point within 1 sample of the discontinuity and applies the correction. The saw function generates the raw value, then subtracts the PolyBLEP correction to get a clean output. Let's look at the difference. On the left, the naive sawtooth and its frequency spectrum. You can see energy spreading into higher frequencies where it shouldn't be. That's the aliasing. On the right, with PolyBLEP applied, the spectrum rolls off cleanly. The harmonics stay where they belong. So now we have clean waveforms, but a tone that just drones on forever isn't very musical. We need a way to shape the sound over time. Give it a punchy start, let it settle, and fade away when we release the key. That's exactly what an envelope does, and it's our next building block. An ADSR envelope shapes how a note evolves over time. Attack rises to full level, decay falls to the sustain point, sustain holds while the key is pressed, and release fades to silence. Each stage uses exponential curves, which sound more natural than straight lines. Here's a clever trick for the attack phase. An exponential curve approaching a target never quite reaches it. It gets to 95%, 98, 99, but never 100. So we aim higher. The attack targets 1.2 instead of 1.0. The curve naturally overshoots past 1, and we simply clamp it. Neat, isn't it? The implementation tracks which stage we're in: idle, attack, decay, sustain, or release, and applies the corresponding exponential coefficient each sample. Notice the attack target constant set to 1.2. When the level hits 1, we transition to decay. We have individual building blocks, oscillators, and an envelope, but they're not connected yet. A voice wires them into a single signal chain from MIDI note to audio output. By the end of this section, we'll be able to play one note from start to finish. MIDI note 69 is A4 at 440 Hz. Each semitone multiplies the frequency by 2 to the power of 1/12. This single formula gives us the entire piano range. The voice's process function is the per sample signal chain. Mix the oscillators, run through the filter, multiply by the envelope. Nothing fancy, the mixer literally just adds the signals together. In later episodes, we'll add modulation and more complex routing, but for now, simplicity is the point. We can play one note, but a synth needs to play chords, and that means managing multiple voices at once. For polyphony, we maintain a pool of 8 voices. When a note arrives, we find an idle voice and assign it. Watch as the grid fills up. Each voice lights up with its note. But what happens when all 8 voices are busy and a 9th note arrives? We steal the oldest voice, the one that's been playing longest. It flashes red, then immediately takes on the new note. This is oldest voice stealing, and it's the most straightforward strategy that still sounds natural. The process block function is where it all comes together. For each sample, we sum the output of all 8 voices. In a future episode, we'll add different play modes: mono, unison, stereo panning, but polyphonic mode is our foundation. Everything we've built so far is pure DSP code. No plugin, no DAW, no knobs. By the end of this section, we'll have a working VST3 and audio unit plugin with over 30 automatable parameters. The bridge is JUCE's audio processor. It's what your DAW talks to. It handles the audio callback, MIDI input, and plugin state. JUCE provides a parameter system called the Audio Processor Value Tree State, or APVTS for short. It manages over 30 parameters: oscillator types, filter settings, envelope times, and more. Each parameter has a name, a range, and a default value. JUCE handles saving and loading these automatically and exposes them to the DAW for automation. Every time the DAW calls process block, we read all parameter values from the APVTS, pack them into our own synth param struct, and pass that to the synth engine. This is the bridge between JUCE's parameter tree and our pure DSP code. The synth then distributes these parameters to each active voice. 4 critical parameters, volume, filter frequency, and the 2 oscillator gains, use something called smoothed value. Without smoothing, when you move a knob, the value would jump instantly from, say, 0.5 to 0.8. That instant jump creates an audible click, like a tiny discontinuity in the audio signal. Smoothed value ramps gradually instead, spreading the change over a few milliseconds. It's a small detail, but it makes the difference between a prototype and a polished instrument. That wraps up Phase 1, from an empty project to a working 8-voice polyphonic synthesizer. We built a Phasor, added anti-aliasing with PolyBLEP, created ADSR envelopes, wired it all into voices, and connected everything to JUCE. Next episode, we'll expand the sound palette, 7 different waveform types, each with proper anti-aliasing, plus a noise generator for texture. See you in Phase 2.